We ended last time looking at signal to noise, and here's a comparison of two CT images of a phantom. It's just something that you print on a 3D printer and fill with contrast, and then you can image it. You know exactly what the shape is because you programmed it, in a CAD/CAM model, so you know the ground truth of this object. Here, when it's imaged at 600 milliamp current, and we'll see this in a minute what that means. It's a lot of photons. We get very uh, essentially smooth characteristic of a background that all is supposed to be the same number. This is an iodinated water, it should all be the same number. If you use far less photons, you can see that there's more uncertainty for each pixel, what its value is, and it just looks like noise, right? It has oscillations that are random. You can quantify what your values are just by putting a region of interest up and drawing a circle. And let's say I don't know, we have about 100 pixels in here, and the mean is 675.9, and the standard deviation is 10. So you have a mean value in the background and then a scatter around that mean value. And over here, where it's noisier, 672.6 is the number. So it's the same value, the same mean value, right? You're going to get, but the standard deviation over here is close to 30. So there's just a lot more variability in the pixel number. So this is how you measure, the various pixel numbers in your image. And if we have a simple image that just has a little circular hole drilled in plastic, and so the plastic is in the background, this should all be the same number, right? Because it all has its same material properties. There's a hole here, so it's air, so it actually should have the number basically minus 1,000 in a CT scan. Should be the same. You can clearly visualize that thing with this signal to noise. It's a little bit harder to visualize it over here when our signal to noise gets lower, i.e. the noise is expanded. If I put a region of interest on this background, say I have, I don't know, about 200 pixels in there. Well, does it say how many pixels? Yeah, I got 20,000 pixels in there. That doesn't seem right. But anyway, um, gives you the mean and the standard deviation. And so it's just I'll show you a formula for it, what the values are around the mean. So here's the mean value seen in this red box. And then these are the values around the mean. So it's the width of that distribution that gives you the amount of noise. We go over here, do it in the same phantom. Everything's the same. So the mean should be the same. Turns out it is the same. But we have a much broader sort of list of pixel values inside that volume because there's more noise, okay? We can quantify the contrast to noise by drawing a profile through a target object, right? And looking at the signal value inside that object. So here our target object is this hole. It has a lower signal value than the background. So when we look at that profile, we say, okay, here's our target value is 115. The background is 200, right? So that's the raw contrast just in terms of numbers. In this one, where we have higher noise value, when I draw that profile, a couple of things happen. There's more variability along the profile, and the contrast of the dark target isn't as low, right? So it's actually 156 at its minimum. So what is the contrast to noise in these two cases? So the contrast to noise is the value of the target minus the value of the background. So here's our target minus the value of the background divided by the standard deviation of the noise, right? And remember when we came back here, the standard deviation of the noise is 3.4 was measured in here. Okay. So in this case, that's 115 minus 195 divided by 3.4 gives us minus 23.5 as the contrast to noise. It's a dimensionless number, right? Because basically the standard deviation and the signal, they're in the same units. And so when you divide them, you have a dimensionless number. Over here, the target value is 156, the background 192 again, divided by a much higher standard deviation measured. When we go back here, this standard deviation is 8.3, right? So that goes in here. So the contrast to noise of that object is minus 4.3. It's a lot less than minus 20, right? And there's a, a general rule of thumb that is, if the contrast to noise is smaller, the absolute contrast to noise is smaller than 5, it's not really good to make decisions based on whether or not you can see that thing, because you are going to be wrong 10% of the time, something like that. Once you get the contrast to noise up to around 5, you can be pretty confident you're going to be right about 95% of the time to call it. And so you can see this is an object right here that has a contrast to noise of 4. And you ask, is that a real object? Like if I didn't know there was an object there and I had to make the call, is that a real object? It might say, well, it looks darker. Yeah, but so does this. So does this. You know, they're just as dark, right? So you're going to make mistakes depending on the contrast to noise. The other image quality thing that we try and improve is called clutter. And here we have a mammogram. This is an X-ray mammogram, and you can see there's a dense piece of tissue in there that is giving us this signal. When we image that with MRI and a contrast injection, right, then just this little core lights up of this thing, right? So we got rid of all of this clutter, which is, it's not that the signal to noise is bad, it's just that there's so much stuff going on that you can't see what you're looking for. Again, here's a mammogram. You say, well, this could be probably a lesion. Here's the lesion after a contrast injection on MRI. Okay. So MRI is spectacular at highlighting lesions in the breast. The issue is that you see this fantastically high contrast lesion, a not small fraction of the time when you biopsy that thing, it's not malignant, it's benign. And so this is the problem. You find these lesions, go after them, biopsy them, but they're many times benign. Right? So that's we'll look at statistical performance on using these things, using images as tests. So this is somebody's just at, as their shoulders turn into their neck. Okay, so there's a bit of the top of their shoulder here. This is the trachea, right? The spine here. These are the carotid vessels coming up the side of the neck. Okay, so they're very large vessels. They feed the brain blood, and they come off the top of the aorta and they come up here. They also have highly pulsatile flow. So the velocity of the blood in here is actually pretty high. And if you put a stethoscope on your neck and you listen, you can hear the blood swooshing by, like whoosh, 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 right? And in MR, if you don't account for the fact that the blood signal is coming through your plane of imaging, and if you don't gate to the heart rate, it's coming through at kind of random points in your acquisition, it really screws up your phase encoding. Like, where is the vertical value of this thing? And you can see it gets spread out over all this stuff. This is called artifact, right? So it's signal, it's not noise, it's not random signal, it's caused by a physical process, but it's just getting in the way of making a good picture. It's called artifact. However, one person's artifact is another person's technique, right? So if you can modulate a signal, so when you see an artifact, you say, well, what is causing this modulated signal? What the heck is that? Then you can actually exploit that to measure something usually. For example, here, this thing is pushing through. If we figured out a way to, get all of this stuff essentially lined up in time, perhaps we could measure the velocity of this thing by this change in brightness, right? So that's called artifact. So you have artifact, a signal that isn't noise, but it's not really supposed to be there, ideally. Clutter is you can have high signal to noise images like Where's Waldo, right? You open that page immediately and you look, and there's beautiful signal to noise, a signal to noise of 100, right? But finding Waldo is hard because there's a whole bunch of clutter, right? And then just flat out noise. And noise is random signal that's superimposed on top of your picture. So we're now going to move into X-ray physics. This is a big jump in topic. Here's a X-ray image. It's a transmission X-ray image of somebody's hand. They just put it on top of a film screen detector or a digital X-ray detector, broadcast like shined X-rays through, took a picture, right? And you can see extraordinary detail in bones and everything like that. That's why this is used a lot in orthopedics, and it's used for mammography because you can produce these super high resolution pictures. If you've got your object right on the detector and you shoot X-rays through it, you get really high resolution pictures. Here's a basic setup of, there are many ways to set up an X-ray imaging system, but here's one basic. I've got a source of X-rays. It's like an X-ray light bulb in there that I'm going to flash on and turn off. And when that flash is on, the X-rays will proceed out in directions through the patient, and the X-rays that get through the patient will interact with some kind of detector. This can be a phosphor screen that shines a light, goes off when the X-ray hits it, or it can be a direct X-ray cadmium telluride detector that has a shower of electrons come out when an X-ray hits that target, right? It's just to have some way to detect X-rays that are getting through. And the contrast is generated by the fact that there are pathways that X-rays don't get through, right? So here, if we look at this bone, the X-rays that were coming down through that bone, a lot of them got absorbed by the bone. And so we didn't get a lot of X-rays hitting our target. Traditionally, this was a film target. So in those places where you get a lot of light or a lot of X-rays, the film gets exposed, and so it goes dark. Those places where you don't get a lot of light, a lot of X-rays, when you put the film into the chemical composition that develops it, those crystals come off and you can see through, right? How many people have done straight up black and white photography on film and developed it in a lab? Yeah, okay. So that used to be something like geeks did in high school all the time. I had a photo lab, the whole thing, but okay. There's no reason to do it anymore. So here's the electromagnetic spectrum. And we're going to be using two locations on this spectrum for this course. Here's visible light spectrum. Your eyes are really tuned to this small set of wavelengths here, 10 to the minus 6 meters in here. So the rainbow's across there. You have infrared, which is what your TV controller uses to talk to your TV, right? The microwave oven is down in centimeter wavelengths, right? And radio waves are meters long, right? And can be tens of meters long, right? For these low frequency radio waves. Ultraviolet light, you can't see it, but it will burn you. So you get a change in your skin. X-rays is what we're going to be looking at, and gamma rays are off the end of X-rays. So X-rays, the ones that we're looking at, usually instead of wavelength, you don't usually talk about wavelengths of X-rays. You usually talk about the energy of each photon. So they come in packets. The photons come like particles. So when you're talking about X-rays, it's convenient to think of these photons as particles as opposed to a wavefront, right? And the particles we're looking at will have energy somewhere between 70 and 140 keV, and we'll see what that means in a minute. MRI is done all the way down here. Normally, you don't talk about the photon energy of a radio wave. You talk about the wavelength of that radio wave because it's a big thing, and you usually have an antenna, and you assume it's a plane wave to do the physics on it. And it'll be somewhere between 30 and 300 megahertz for human scanning. Okay. This is how we make X-rays. This is a toy X-ray tube. It has a disc, and this disc can be made of tungsten or it can be made of molybdenum. And it's the target or the anode. So it's a positively charged anode. And this is a motor that spins this anode at a high rate, like 10,000 RPM. And down here is a coil. Inside this little cup here is a coil that you pass a lot of current through, and it heats up the coil, and electrons boil off. And you put a large voltage between the anode and this is a cathode, and those electrons will fly across and hit the target. And then when those electrons hit the target, most of the time, 99% of the time, they just heat the target up because they're just banging around inside the target. But every once in a while, one of those electrons interacts with an atom in the target, and it will change its trajectory just by a glancing collision and cause an X-ray to come out, right? That's called Bremsstrahlung. So here, this is more like the graphic I'm going to show you. Anode, big motor to spin that anode fast. Here's the electron source. I've got wires going in here providing current, right? And we've got a big voltage between this and this cathode. This is inside a vacuum so that the electrons don't heat up the gas or vaporize it or whatever. Yeah. Oh, the reason it spins, that's a great question. If we left it stationary and we turned this on and we had electrons flying across here hitting the target would melt. So you want a lot of X-rays coming out. To get a lot of X-rays, we need a lot of electrons to hit it, and it gets really hot. So basically you increase the effective area that you're irradiating, or the sort of energy that's deposited in the target goes down, right? So here's the graphic. We have this coil that's going to, when we put tube current through this thing, and this is a dial we have on a CT scanner, I can just click the tube current from 50 MA to 100 MA to 300 MA to 700 to now 1400 on our new scanner, right? We used to be stuck at 7. Now we can get up to 1400. And that produces a lot of X-rays. So a lot of current goes in here, a lot of electrons come across, fly into the target. This is our big motor that's rotating the target. The voltage between this and this is somewhere between 70 and 140 kilovolts. So it's a high voltage, right? The electron, once it boils off here and flies across this gap, if it's 140 kilovolts across the gap, by the time it goes from one side of the gap to the other, it's just about to hit the target, its velocity is giving it 140 kilo electron volts of energy. So if you write down the energy equation of something flying through, you can, energy unit is a electron volt or kilo electron volt, okay? So that's what the energy of the electron has when it hits the target. Not all of that energy will come out as 140 keV photon, right? But we'll see there's an interaction in there that produces some stuff. So this is also at a very high temperature, this filament, when it's being run up. This is why when you get on a CT scanner, normally the procedure is before I scan a patient, I run this tube a few times, just warm it up, right? Get this cathode warmed up, get this thing warmed up so everything comes into a stable configuration, right? So what happens to those electrons? What we're going to look at now is, imagine I'm an electron and I'm flying across this 1 inch or 1 centimeter gap, and I'm going to hit a target. So here's my electron flying into the target, right? And these are the atoms in the target. They could be tungsten, as we saw, molybdenum. Most of the time, they're just going to bang into an electron that's in the atom, fire that electron off of that atom, change their trajectory so the momentum is preserved, and then hit another atom and do it again. And so you just get a shower of electrons that are happening from the incident one, right? And that just causes heat. The electrons are zipping around in there, heating things up, right? So that's of no use to us, but that's sort of 95% of what's going on in there. The other thing that can happen, let's start with this one. This produces most of the useful X-rays for us. An electron flies in here, it gets close to either the nucleus or an electron, and it doesn't hit it, but it is affected by the charge such that it bends its trajectory. And when you accelerate a charge, right, that causes electromagnetic radiation, right? We've all did that in high school, right? You accelerate charges, you cause electromagnetic radiation. So if you accelerate this electron and it takes a hard left turn because it got really close to a positively charged nucleus, it got right close to it, then what happens is it fires off in a new direction. It has a new speed, right? So its speed slows down and an X-ray comes off and energy is conserved in that collision. So when you add up the energy of this X-ray and this electron that had this glancing blow, it is the energy it started out with. But what we've generated is a X-ray, right? So that's how the X-ray got generated. And most of the X-rays we're going to use in the patient are generated this way. It's called Bremsstrahlung X-rays. Another way that X-rays get generated is an electron comes through and it knocks out one of these very close electrons that are in a K-shell orbit. So that's an orbit very close to the nucleus. It's the lowest energy. It's right in the energy well of right next to the nucleus, right? If this has enough energy to knock it out, and it does so, that thing comes out. This K-shell electron comes firing out of here. An electron at a higher orbital, farther away than the lowest energy state, will drop into that state. And when that drop happens, it fires off a photon because of the loss of the energy, right? So that photon comes out, it's called a characteristic X-ray. Yeah. Yep.
So is the X-ray emitted because of a steep turn?
Yes.
And so the loss of energy
Right. So the question is here, why when an electron takes this hard turn, does it radiate a photon? What is that? So this is like a collision. This is like nuclear physics collision where I have this charged particle coming in, another charged particle. This one gets close and it accelerates really hard. So when you accelerate a charge, you are going to radiate radiation, right? This is one of the big mysteries of the simple model of the hydrogen nucleus, was if you have these electrons around a positively charged nucleus, and I have an electron, say, in the K-shell, and it is zooming around, if it actually is a particle that is zooming around, wouldn't it be radiating energy all the time? Yes, it would. And it would last about, a billionth of a picosecond. It would just fall into the nucleus. And so that was the big conundrum in quantum mechanics. And people still really don't know why. The K-shell electron is a stable place that an electron exists. But it's certainly not a particle that's like zooming around. It's not modeled well that way because it would radiate all the time. It so happens when you do this collision, that model works just fine, right? So when you slow this electron down and it's bent, its momentum now is going up, the energy that is contained in this photon is that loss of energy and that momentum, right? So to get us back to what we originally had with the electron flying in. So this is what the Bremsstrahlung radiation looks like when you graph how much do you get at each energy, okay? So, excuse me, this is X-ray photon energy across this axis, so going to higher and higher energies. And this is the relative number of X-rays emitted from our target, okay? And it's just normalized. You could say, we'll normalize it so the integral under one of these things is 1. If on my X-ray tube, I set the voltage between the anode and the cathode. I just changed my voltage dial to 100. Okay, so the highest energy X-ray that I can get out is 100 keV, right? That means that electron that had 100 keV going across the gap, all of its energy got transferred into an X-ray photon. Okay, that is a highly unlikely collision because you would have to have the electron go straight at the nucleus and bounce off, basically, come right back at you. That doesn't happen too often, right? If you think, how often would that happen? The nucleus is really small. What happens much more often is it just misses the nucleus and makes a turn. And then lower energy X-rays are emitted when that happens. And that's much more likely. The most likely is it makes a turn such that the electron, or the X-ray photon that comes out, in this case, I set this to 100. The peak of this thing is sort of like 45 keV, right? However, I'm getting photons all the way up to 100, just with less frequency. So this is called a probability density function, and it means like the relative number of photons at that energy that are coming out of your target, right? These tiny little lines here are those characteristic radiation for tungsten, for that atom, for the K shell electron, right, is here, and then this would be the next one to the K shell electron. You get a spike, but it's a small fraction of the total number of photons that are coming out of this thing. So if I click now, I say, I need some more high energy X-rays to image this person. I click my voltage on my tube up to 120, and voila, I get a lot more X-rays at 100, right? So I have a lot more high energy X-rays to image that patient. Why would I want to do that? As patients get bigger, like the size of people is quite different, right? As they get bigger, in order to get any photons out of the patient, you need to crank the energy up so that they have a hope of getting through the patient. Because as we'll see, higher energy X-rays travel farther through water, through muscle, through bone. They're attenuated less often than lower energy X-rays. So down here, when we look at the energies coming out of this tube, we see that the relative frequency of photons at these lower energies goes down, down, down. And the reason is that those photons that have low energy are much more easily absorbed by anything. So they get absorbed by the target itself, by the glass that's holding the vacuum. Excuse me. We will put a tungsten, or we might put a copper filter on it to filter out a lot of these low energy X-rays. If none of that filtering was happening, it was all bremsstrahlung, this curve would just keep rising up to go up to here. But the low energy stuffs get filtered out. That's good news. And we purposefully do that such that we don't dump a lot of photons into the patient that have no hope of getting out of the patient, because that doesn't generate any contrast or any information, right? It just generates dose. So this is the X-ray spectrum from our X-ray tube. Each tube has its own spectrum, right? When you buy a new tube, they don't give you this diagram, right? This is something that's sort of held close to the chest by the manufacturers. It's like, what is our X-ray spectrum? And they'll put filters in front of the X-ray beam to tune up their spectrum, right? Okay, so what happens now? We've got X-rays coming out of our tube, right? And they're coming out at all these different energies. What can happen to those photons in the patient? It gets a little confusing because this diagram looks a lot like what happens to electrons when they hit the target, right? It's a collision. Right now, we've left that behind. We now have X-rays coming out of our tube. The X-rays are going to go through the patient. There are going to be collisions in the patient, right? The X-ray is going to collide with atoms in the patient. So here's our incident photon. This is an atom inside the patient. And we ask, well, how can the photon be absorbed by the patient? And there's two main ways. One's called the photoelectric effect, and one's called Compton scattering. And we'll see these are quite different, different energies. Once we get to a certain high enough energy, everything becomes Compton scattering down at like 100 kilo electron volts and below. A lot of the absorption is the photoelectric effect. And so let's see what happens here. An incident X-ray comes in. It interacts with an electron in the electron cloud around the atom inside the patient. Could be water, could be protein, could be some carbon thing. Interacts with that, and a photoelectron is ejected, and then characteristic radiation can come out. Okay? Ideally, this characteristic radiation is at an angle that your detector doesn't see, right? And this photoelectron is just going to go on, interact with the patient some more and deposit energy, right? And so what has happened effectively is our photon came through and it just disappears in terms of our detector, right? And that's ideal. We want along a line from our source to my detector element, I want photons to either be absorbed completely or get through, right? And then that gives me contrast in my picture. The characteristic radiation can come out as this electron that was ejected, others drop in to fill the energy and they emit this radiation. Or when the others drop in to fill the energy, interestingly, instead of a photon being emitted, they can emit an electron, right? It's sort of this is a much lower probability process, but it works because all the energy is conserved and everything. So it can just eject an electron to instead of this characteristic radiation. Compton is different. X-ray comes through. The X-ray interacts or has a collision with an electron. You have a question? Oh, the Auger electron is an electron that when the X-ray comes in, ejects the photoelectron through its collision. Okay, so the photoelectron shoots off into space. I now have an empty orbital in my atom. And when an electron drops into that orbital, energy is released from the atom. The energy can come out as characteristic radiation, or that energy can actually come out as another electron, right? And the details, the quantum details of how this happens, I can't help you out right now, but I'm sure ChatGPT would draw a beautiful diagram of how that happens, which I will do later. And any good question we get, I usually go, and I don't know precisely how to answer it well, which is like, how does an Auger electron, like it doesn't, I don't think an Auger electron emerges, right? It's not created because we don't have enough energy for that. It's an electron that's in that atom, but it just gets shot out to keep energy conserved. You can have electrons emerge, right? If you have a photon that's got high enough energy, right, you can create an electron-positron pair from that photon. That will happen, right? And that's at up around 511 MeV, which is the rest mass of an electron. So anyway, let's go to Compton. Coming through here, there's an electron that interacts with the photon. It gets boinked out of its orbital, and the incident photon is just deflected at an angle. So its energy goes down, right? So it becomes a lower keV photon, and it changes its direction. Right? This, if it changes its direction enough, we're in the clear because it will interact. So the original photon comes through, hits something inside the patient. The Compton photon after that collision comes out at an angle and misses our detector. That would be great news, right? It's not good news for somebody standing next to the patient, right? If that's why you don't stand next to people getting irradiated, because a lot of stuff comes out of them in different angles and things like that. And so if you do stand there, you're usually covered in lead. So when you're doing fluoroscopy, the physician has a big lead apron because of all the scattered radiation coming off the patient. And the most common reason why people have to retire from interventional cardiology and interventional radiology is, guess what? Nope, spinal problems from because you're wearing this darn lead, right? So you got this 40-pound thing, right? And so their knees and their spine and everything get all messed up. Yeah,
This is where we're not getting a signal on our detector.
correct. This is how the photons that we're generating, that let's say they're on a line or a beam and they're going through the patient, how do those photons get absorbed? That's what we're talking about. Let's say half of them get absorbed, half don't. We're going to make a picture, right, of, where does that happen? Yeah.
Because of the Compton photon that it just misses the detector, but for the characteristic radiation, you said that the angle changes and then it still hits the detector, but it can't do that.
Well, it can, in either case, it can hit the detector or not, right? And as we'll see, we're going to set something up in front of the detector such that if something comes off at a weird angle, we're not going to measure it. It's going to get absorbed by an anti-scatter grid. These are all called scattered photons, which we don't want. Like, it's just a big cloud. It makes a big fuzzy blur. It's just like a flashlight going through your hand. When you see the image on the back, it's not a clear picture of your hand. It's just a big fuzzy cloud, right? Because everything's scattered so much. These are all scattered. That's light. This is X-rays scattered. Okay, so the two effects have an interesting dependence on the stuff in the patient, like what a patient's made of, right? So the probability of a photoelectric interaction with an incoming X-ray and an atom goes as the fourth power of the atomic number of the element. So as the element gets bigger, right, the photoelectric effect for this term goes up much higher, okay, for a fixed energy of photon here, right? And I can't tell you why it's a fourth power just off the top of my head. It's not a simple explanation. It's somewhere between the third and fifth power, depending on the photon energy, depending on a lot of things, right? Depending on the atom itself and the size of the K shell. What happens is as the Z gets bigger, you get a bigger and bigger nucleus, and the K shell electron, which is causing a lot of this photoelectric effect, gets closer and closer to the nucleus. And this causes this effect to go up as the fourth power. It's just the change in that orbital. Also, as the energy of the incident photon goes up, the photoelectric effect goes down, okay, in terms of its relative frequency. Remember, this is the probability of that thing getting absorbed. For Compton, it goes as linearly with Z. So as Z gets bigger, the Compton effect gets slightly bigger. However, over the range of energies that we're going to look at, the Compton effect is relatively constant. Okay, and we can, instead of looking at those formulas, this graph is more illustrative of what you need to know. So here's energy of photons, energy of incident photon here. This is called a mass attenuation coefficient. And so if this is a big number, a lot of X-rays get absorbed. Okay, and we'll see how this gets used in a formula in a second. But if this number is big, there's a lot of photons getting absorbed. This curve here, this curve right down there, is the photoelectric effect, the relative amount of mass attenuation coefficient, or the relative amount of X-ray absorption, right, as the energy is changing, shows like this. So as we get to higher and higher energies, we see this is a log scale, remember? So this thing just goes diving down such that by the time we're at 110 keV, very little photoelectric effect is stopping X-rays. Okay. If we're down here at, this would be 20, 30, 40 keV here, we have a significant amount of photoelectric effect. This curve here is the Compton interaction curve. So you can see that over the course of our energies that we're looking at, our Compton absorption is roughly constant, right? So this actually gives you a great idea, right? Which is, hey, I could take two pictures. I could take an X-ray image at this energy, say 30 keV, and it would roughly have equal photoelectric effect and equal Compton effect, right? Then I could take a picture up here at 110. That looks like 200, like 110. And here it would be all Compton. So now I have two different types of interaction occurring. It gives me different contrast in the pictures, right? So it's now the pictures become a two-dimensional picture. And this is called dual energy X-ray imaging. It's a great thing to do for a project. It goes on to multi-energy X-ray imaging. But anyway, that's the idea there. So back to our X-ray imaging system, we have ideally a point source of X-rays up here. It's not exactly a point. If it was a point, it would obviously just burn up, right? Because you would have to have all of this energy down at a single point. So in fact, it's sort of a rectangle. Okay, so there's a patch on the anode over which the X-rays are made. Okay, and the patch is usually 1 by 1 millimeters, 1 by 2 millimeters, something like that. We put a filter in to get all of the low energy X-rays out so that they don't ever hit the patient. We transmit X-rays through the patient, through the table, which is basically X-ray transparent. There's an anti-scatter grid here so that if my X-ray is coming through this way and it interacts with the patient and it causes a Compton scattered photon to come out this way, I don't want it to hit the target over here, right? Because that's just random noise. So if it's coming at this angle, it can't get through this anti-scatter grid. It gets stopped. And you can imagine how you do that is you make tiny little holes that look back at the target. And so at any detector, if I look back at the target, I can only see the target through that one hole. Everything else is going to get absorbed. Yeah. It is. Yeah. So the question is, if this is going to work, then this detector and the emitter would have to be in a constant orientation for that anti-scatter grid to work. That is actually true. So the question then is like, when I go to the dentist and they put that stupid thing in my mouth, I'm going to chomp down on it, right? And I have an X-ray beam obviously pointed at my head. Like, what happens with this scatter grid? My anticipation is they don't use an anti-scatter grid there because the detector is right up against the object. You are lying the object on top of the detector. So if I took this person's teeth and I laid them on top of this detector, you'd get a beautiful picture of their teeth, right? So that's how that works. That's a good question. So we're going to talk a lot about the intensity of the X-ray beam. It is proportional to the number of X-rays or the photon fluence rate, which is the number of photons per unit area per unit time. Okay, so I just the amount of photons that are coming out of my source multiplied by the energy, because the higher energy photons are going to deposit a lot more signal on my detector than the lower energy photons. And so the intensity is proportional to the energy of a photon times the photon fluence. Okay. The total photon fluence, as you can imagine, is kind of complicated because we have this diagram, right? If I set my voltage to 100, then all of these energies are coming out here. So my total fluence is going to be the integral under this curve, just adding up all of these energies with the relative weightings given by this curve, right? That's the relative weightings, and then we're just integrating the energy. So the intensity, I multiply, as I go up in energy, I just multiply the energy such that these photons carry a bigger bang, you know? And so the intensity, I put that in there. When I integrate that, I get the total intensity. Okay. So how are X-rays attenuated? Sort of macroscopically, how are we going to model this attenuation? We've seen how it happens on an atomic level with a lot of hand waving and things colliding with electrons, etc. So what happens if I look at a macroscopic sample? So here I'm going to have a magical X-ray tube that produces parallel beams of X-rays coming this way, and I'll have 1,000 X-rays hitting this target. This target is 1 centimeter of water. Okay, so the X-rays come up. I put like a two-dimensional thing. It's 1 centimeter deep, and they go through. So some of the photons go through, some of them get absorbed. Okay, and when we do that experimentally, we just do that. We find out with 1 centimeter water, 800 of the 1,000 photons come out the other side, right? And 200 are left in there heating up this water, right? Or shooting scattered X-rays out of the target. Then when I go, I've got 800 coming out here, I'll put another 1 centimeter thing here. Again, 20%, the probability stays constant. So the probability of interaction is 20% of these are interact. That gives me 640 coming out, right? Again, put it in there. 20% of that coming out the back end is 512. Okay. If you plot those numbers, right, 1,000, 800, 640, 512, and you just take a look at that curve, it's fairly obvious what it is. It's a decaying exponential. It's a mono exponential, right? It's proportional. The amount of decay here is proportional to the amount of stuff it has gone through, the total distance. We'll call that X. So it would have gone through, let's say, 1 centimeter, 2 centimeters, 3 centimeters would be the values of X there. It starts out with 1,000. The number I have left by the time I get out here is that 1,000 multiplied by this exponential decay. This, if it's water, the mu value is whatever that is for water. If it's bone, you replace the mu value for bone. If it's aluminum, you replace the mu value for aluminum. So that's a material-specific constant. Okay, so depending on the material, we'll see different exponential decay curves. For metals, like aluminum, the decay will be very, very fast. The X-rays will disappear more quickly. If it's air, the decay will be very, very slow, right? And so you'll see the points, and mu will have a very low number as opposed to a high number. It's called the linear attenuation coefficient. The mass attenuation coefficient is often what's given so that you multiply by the density of the stuff in order to get the true attenuation, okay? And you can derive from simple first order argument that, you know, this is the change in number, like the delta n is going to be, well, you know, your first guess would be it would be linearly proportional to how thick the sample is, right? Kind of makes sense. It's linearly proportional to this thing by definition. And then when you set that equation up, it's like a simple mono exponential. Just like any first order differential equation, like a glass of beer on the table, the rate at which it's warming up is proportional to the temperature of the glass itself, right? So the change in temperature is proportional to the temperature, or the temperature difference between the air and the beer. And when you set that equation up, it's a simple mono exponential, right? Same thing here. It's hard to remember these values because they have strange values like 0.3861 centimeters squared per gram or something like that. So it's hard to remember that. So normally what people in this business carry around with them are half value layers. And so you say, well, how much water do I need to reduce the photons at this energy by 50%? Right? And that's a thickness now. It's in centimeters, and that's the half value layer. Right? So that's the thing normally you carry around with you. Like, what is the half value layer of muscle, water, bone, aluminum, things like that. Right? And it's a simple relationship between mu and the half value layer, obviously. So here's a few examples. Different energies, different energy photons will have different half value layers. The higher the energy, the deeper that photon will go into the sample before it gets absorbed usually, or the farther it goes, because the probability of interaction drops as the energy goes up. Until finally you get to gamma rays and you are basically transparent, right? So if you stand in front of a gamma ray source and you have a gamma ray camera back there, it's just like, all you see is the gamma rays, right? The ones that get left behind are few, but they do a lot of damage, right? So if they actually hit something, and it's very rare that they hit something, but they do a lot of damage. And that's what radiation therapy is, right? So if you have a small little tumor and you want to kill just that tumor, you fire gamma rays at it in a very like nicely crafted beam that just covers the tumor, and then you shoot it from all different directions, right? So that the pathway in and out doesn't get irradiated much, but the tumor itself gets a lot of radiation. It just all piles up there. And it's usually a big gantry that goes around the patient like this, and you basically kill that tumor with radiation, right? Usually gamma rays. But you can drop the energy down. So here, let's look at muscle and bone. So at 30 keV, the 50% of the x-rays are gone by 1.8 centimeters into the muscle. Okay, so about that far. Okay. And if we go up to 100, I've got to go 4 centimeters to get 50% reduction. Okay. So this is all kind of making sense, right? Why we're working at this energy is that those dimensions are kind of what we need to cause a good differential between places that have low X-ray absorption and places that have high X-ray absorption. I'm going to skip over this. It's a simple formula. This is why we introduced the local contrast as a fractional contrast, because the expression of that contrast comes up to be very simple when you've got this geometry. But I'm going to keep going because we got to move along here. What's really interesting, and this is how we get to CT, is like if I have a source of X-rays and a path through the patient, okay? So I have a point source up here. Ideally, it's a point. I just told you it's actually a rectangle, but it's a really tiny rectangle, so it's sort of a point up here. That beam goes through the patient and hits my detector, which is in a fixed orientation with respect to the source all the time, right? So the question is, okay, you guys hear me out there in the nether sphere? Thank you. Okay, so let's go along this pathway. Basically, the linear attenuation coefficient, as I move through here, will change as I'm going along the path, right? So if I'm in lung, the linear attenuation coefficient for that small, cross-section of that path, as I'm going through, the linear attenuation coefficient is very low. And then when I hit a vessel, because it's got contrast in it, boom, it gets very high, right? And then as it crosses through that, so a lot of X-rays get dumped in there. And then as I come out here, it gets low again, and then I hit bone, then I hit muscle and fat all the way through. And so the way you model that is with a function that is the linear attenuation coefficient as a function of position along your pathway. And what we're going to do is we're going to integrate those values all the way through the patient on that trajectory, right? And that will give us our total amount of X-ray absorption for that path, right? We're just adding up each little box. So if I think of this thing as a ton of little 1 by 1 by 1 millimeter boxes, as I go through each box, I just evaluate what's mu, how many photons get left behind, go to the next box. What's mu, how many photons get left behind, go to the next box. So I'm just doing that integration. And that gives me a number out here that I see on my detector. I start with N naught, that came out of my source, and then I get N, which is smaller than N naught, always, right? Because things get absorbed. And I can calculate what that is if I know these values, right? How are we going to know those values? That's the whole point, is that the image is going to be these values. This is really cool. This is where it gets cool. So now, if I have an image that has this value of every point inside the patient, well, that would be great, right? Because it tells me what that tissue is. Basically, it's a number that is different for different tissues. And so we're going to see how we get there. So the total intensity at my detector, if we really want to go whole hog, remember, we have to take into account we have this distribution of energies, the energies themselves, and then the amount of absorption of those photons. But hang on, the absorption is going to be dependent on energy, right? So different energy photons will have a different mu value, as we saw in that table. So if I want to do this perfectly, I have to know mu at each point, but also the various mu values for each energy, right? And that becomes very hard, right? So we're going to skip around that and pretend that the beam is actually at one energy, and we'll call it the mean energy of that distribution, and we'll go from there. But if you're going to do a big Monte Carlo simulation of that's exactly what's going on inside, you need to actually use all of this stuff. Huh. Let's see. There we go. Not sure why that did that. So here, this is why you remember half value layers versus the attenuation coefficients, these mu values, because here they are for air, water, bone, muscle, lung, and brain at 20 keV and 100 keV. And this is a typo. This is not 0.4. For bone, it's 4. But you can see there are differences, but they're relatively small, right, between these objects. And then you get to 100 keV, the values go down because at 100 keV, more photons get through the patient. All these values are measured to many decimal places by NIST, which is this really cool place in Montgomery County in Maryland. They do all of these physical measurements. So here are the linear attenuation coefficients as a function of photon energy plotted on a graph. It's a log-log graph, and you can see bone, the attenuation coefficient going down with energy all the way to 100, muscle, soft tissue. So if we're going to make a picture that has different values for different tissues, it's this difference which is important to us. It's the difference between bone, muscle, and other soft tissues, right? I could have every tissue down here. We're usually going to be making pictures up here. Sometimes we'll make pictures around here. We're going to put on that same curve, we've added some other things. Hypake is a contrast agent you buy in a bottle that you can inject into a patient. And as you can see, its linear attenuation coefficient, because it's a high Z molecule, right? It's usually iodine, which has a Z value like, I don't know, What is iodine? Anyone know? 38, 53, something like it's big, right? Compared to carbon. And so that contrast agent has a very high linear attenuation coefficient, which will cause a lot of contrast between it and the background. This barium sulfate mixture is here. That is like bone, right? And remember that picture of that guy looking at the milkshake, like, he has to drink that milkshake. That's what's in the milkshake, this barium sulfate. Well, there he is again. He's like, oh, I don't know. But this is what it looks like when it's inside and you want to track through bowel and stuff like that, is to try and see. So if you see some really weird indentations, you know what's going on there. And then here I think I showed you this before. This is like hypake, which is a contrast agent that goes straight into a vessel and causes a lot of shadow because the mu value is very high, right? Here's coronary angiography in the head, not coronary, I mean angiography in the brain done at 2 energies. So you take 2 images and you inject this contrast and subtract them, and then all you have is the vessels. So we're gonna, what time we have? Well, you got 20 minutes. Oh, good. So what do the detectors look like? If we have basically photons coming in and we want to detect where they are, you can think of it as a camera, right? I have a two-dimensional array of detector elements, and the photons are going to come in and hit those elements and make a two-dimensional picture, right? Each element traditionally looked like this. You have an anti-scatter grid such that photons that are scattered and coming at a big angle get absorbed by the anti-scatter grid. Those that are coming straight from the source come down and they cause a scintillation in some kind of solid state material. That scintillation gives off light. It's like poof, literally a flash of light. You put mirrors on the side here so that the light stays inside each energy integrating detector, right? You don't want the light, for example, spreading over to this one, right? And here, if that X-ray came down here, this is a photodiode which sees visible light and turns it into a voltage, okay? And then the voltage is measured back at electronics. And so you get voltage blips from your energy integrating detector, and a voltage blip corresponds to X-rays hitting your target, right? Or your detector. Photon counting detectors work slightly differently and have some advantages. The first advantage is that the photon interacts directly with a cadmium telluride, or there's other materials, but it's a semiconductor. It acts directly with it. It doesn't create a light flash. It creates an electron cloud. So when it hits the detector element, a little burst, a tiny little burst of electrons is created. They are much smaller than the dimension of the anode that is down here that's charged up, such that as soon as that happens, the electrons just go right onto that anode and cause a pulse, right? And so this is direct X-ray detection versus I'm going to make my X-rays, make something flash, and I'm going to detect a light and cause a voltage. This is called photon counting CT. The really nice part about this is that if you get a blip that is a bit small, right, considered small, then it could be for a couple of reasons. One is it might be a scattered photon that's coming in very oblique and it has much lower energy because it's been scattered at an angle. When it fires off and causes a blip, that blip will be below a threshold. You can set a threshold and just say, you know what, ignore all the blips below this number. They're scattered, right? I don't want to see those. I just want to see the blips that I know are from a photon that just passed straight through this patient and caused a nice, big cloud of electrons, right? The other thing is that with that threshold, all of the electronic noise and random signal from electronic noise can be below that threshold as well. So now you've got something that's truly a binary output that's photon, not photon, right? If we go more sophisticated and we say, okay, now we're above a threshold, what is the relative height of the peaks above the threshold? And so it turns out the height of that peak is pretty well linearly proportional to the energy of the incident photon. So now we can divide up our detection such that I'll say I'll have 4 buckets: low, low, mid, mid, high, and high energy. And so I'll have 4 energies in my detector buckets. I'll make 4 different pictures right at those different energies, right? And that just comes with the technology because the amount of electrons you get is proportional to the energy of the incident photon. Here's a traditional energy integrating detector. This is not a photon counting detector. These little chips here, there's 32 elements along here. Each element is about a millimeter. And this is in the Z direction. So the patient, if you had a patient over top of this, their head would be here. They'd be lying like this and their feet down here. Okay. So this is the Z direction from left to right, going through the scanner. This is the anti-scatter grid that clicks down on top of this detector grid, such that photons coming through this way just get stopped by the grid. Photons coming straight from the target will go through. And then this generates a little flash of light, and then there's a photodiode and signal goes out. 256 points along here, along the Z direction, right? And then there's 1,000 points in the orthogonal direction. The X-ray tube is with a fixed orientation to that grid, right? The two of those things, the X-ray tube and the detector grid, rotate synchronously. They're on the same gantry. They're attached to the same piece of hardware. It's a big ring, and that ring spins around the patient. Okay. And the modern scanners, the ring spins 4 times a second. So 4 complete revolutions a second. So it's pretty fast for something that's very heavy. And the G forces for like materials out here and stuff are sort of 50 Gs, 75 Gs, depending on how fast you spin the thing. So you have to build it pretty securely, and because it's under a lot of force. And that's why big companies like General Electric, Philips, Siemens make these big machines. Okay, that one. We have 12 minutes. Perfect. Any questions up to that? Okay, great. So now we're going to look at how we mathematically describe pictures, which will help us write down how you make a CT image. So this is our picture, an example of one. This is a 2-dimensional picture. I have X and Y here. Each point on here, I could have 256 by 256 points, has a different brightness, and we make this picture. We can also make a 3D image such that instead of say a 1 millimeter by 1 millimeter voxel here, I also take into account how thick the voxel is. So if I have a 1 by 1 by 1 and I stack them all on top of each other, I now have a 3D image, right? Or a 3D object. Once I have a 3D object, I can cut it in any orientation I want, right? So it's nice to have a 3D object, then you can go through and check things out in any orientation you want. Mathematically, this is going to be our fxy. And basically where we headed with this is the following. Here's my input. This is my object creating signal. Okay, so that input could be those X-rays coming out of the patient, hitting my detector. That's my input. Is that air, the image that's in the air right above my detector? That's the truth, right? That's my input, right? The other input is in MRI, for each little volume, one by one by one, I will have a frequency and a phase of the RF signal coming from that little object. Okay, so that's my input. For another way of doing this is like if I have that ball bearing and I put it in the scanner, right? And I take a look at that mathematically, that's my ground truth input object. And then I run my scanner and I get an output for that ball bearing. So this is what's displayed on my scanner after all the reconstruction, sampling and reconstruction is done. I get something, looks like this. So I know what this is if I'm testing the scanner. We don't know what this is when we're imaging somebody. We're trying to figure this out, right? But what we want to do is try and characterize what does our system do to this input? Is there a way of mathematically writing down what, if I have this input, what this system is to generate that picture, right? So that's where we're going. We need to come up with a system function that says, oh, if I have this, this is what's going to come out of my scanner. So remember, if this is a noise-free image here and I have my little dot, and this could be in MR or in CT, I got that little dot right there. The output could be this Gaussian blob function, right? And so the question is, what is the system that generates from this little dot this Gaussian blob? How do I mathematically, write that down so that I can make sense of this stuff? So we're going to use something called the delta function, Dirac delta function, a lot. And it's for good reason. It is the mathematical embodiment of that tiny little bead that we're putting in. So we need a function that is like a point, right? And the Dirac delta function is basically a point. And what this is a very trivial definition of it, is that it's a function such that at x and y at all points in space, that function is 0, but it is not 0 at the origin. Okay, I'm not telling you what it is. That's not how it's defined, but it isn't 0 at the origin. What happens is if you have a function, here's your picture, like that brain that we had on the previous page, right? And I multiply that picture by the Dirac delta function, and I integrate over the whole plane. What comes out is sifted out is the value of your picture at 0, 0. Okay. This seems pedantic, right? You're just like, well, why don't you just give the value of 0, 0? Like, why do you need this delta function? We'll see why mathematically using a continuous function, this delta function, is kind of important for the calculus of how all this spills out. A way of thinking of what a delta function is also is the following. So that little bead that I had, if I drew a profile in real space through that bead, I would have 0, 0, 0, 0. And then as I go through the bead, non-zero. As I'm traveling through the bead, and then it comes back down 0, 0, 0, 0, right? Okay, so it's basically a top hat function with a very high peak. I can make a delta function by doing the following procedure. I'm going to cut the width of that function, that top hat. I'll cut it in half, and I'll double its amplitude. So now it's a thinner dollar function, right? But what I'm going to make sure is that if I integrate across it, it's normalized, right? So the integral is always the same. It's always normalized. So now let's cut it in half again and double the peak again. Cut it in half again, double the peak again. Eventually I get this thing. It's a thing that is so narrow that as you integrate across a function, it sifts out a value from that function. And you can plot this thing in 1D. So if I just go along X, whoop, it's non-zero at the origin, and then I keep going, right? So I don't give it a value at the origin. The only thing I know is if I multiply that thing by a function and I integrate across, it sifts out the value of the function at the origin. That's what it does. Okay. If I need to use it in 2D, well, I can just describe it, in the XY plane. If I need to move it over here, we can just subtract, those displacements, eta and psi, and just put it in the argument to the delta function. That just moves the delta function over here. This is called a sampling comb, and this has a whole bunch of delta functions. So now I have a delta sub s for sampling. It's a continuous function of x and y in the plane. Okay, there's a value. It has a value everywhere in the plane, right? And I have these constants, which are the separation of the spikes or the delta spikes. So that when I integrate this thing, if I multiply a 2D function by this and take that integral, I get the values of the function at those points, which is very useful, right? Because that's like sampling a function, right? So if I have this continuous function, I say, I really want to load that thing into my computer. I need to get values of the function and load those into the computer. And so to do that, we need to sample that function, right? And then we use this to generate values. And then in X-ray, what's going to be very useful is this type of delta function, which is a line. It's defined everywhere on the plane, everywhere in XY, it has a value. A lot of those values are 0. If I multiply a function by this thing and integrate, I get the value of the function along that line. So it's like a bunch of samples along the function along one line. And it turns out we're going to do that a lot in CT. We're going to sample lines through the patient, right? So we need this mathematical thing. And so the line is given here. It's parameterized. It's defined at each point in the plane such that this is true, right? So all x and y values such that this is true, and you get this line, okay, non-zero there. Okay, we'll do this one thing, okay? This is quick. We're going to use this function a lot too, as well as the delta function. This is called the rect function. So it's 0 up to -0.5. After 1/2, it's 1. And then, or after -1/2, it's 1. Then after 1/2, it's 0 again. And so that's its definition, okay? You can imagine this is a very useful function for saying multiplying something if you only want to look at a particular domain, right? So it gets used a lot. And then this function is called a sinc function, which has a peak, and then it sort of has these wavy wings that go along like this. It oscillates like a sine wave. Here our frequency is 1, so it's going through this way, right? It also decays as x gets larger. Fascinating. As x goes to 0, it does not blow up, right? So the ratio of sine x over x as we're going into 0 goes towards a constant, right? Because sine x, when x is really, really small, it equals x. So that's why it doesn't blow up here. We have this thing. Fun fact, when you take the Fourier transform of this, you get this, right? And so you basically, if I have a square in image space, I say, well, what's the Fourier transform of that block in image space? When you go to the Fourier space, it looks like this. And that means the inverse Fourier transform of this is this. This is going to come up a lot in mostly in MR. Okay, you're going to get to know a bunch of Fourier pairs. And one of them is a rectangle function has sinc as its Fourier pair. Gaussian has a Gaussian as its Fourier pair.